Hello everyone. Welcome to Marri Laxman Reddy Institute of Technology and Management, Dundigal, Hyderabad. This is S. Rajkumar, Assistant Professor for the Department of Electrical and Electronics Engineering in Marri Laxman Reddy Institute of Technology and Management, Dundigal, Hyderabad. In this lecture series, today I am going to explain about parallel LC circuits. In that parallel LC circuit, the locus diagram of parallel LC circuit by varying XC in the capacitive reactance. By varying the capacitive reactance. So, how to draw the locus diagram of a LC circuit. So, this is the topic we are going to see in this lecture. So, for this one, so just you consider a parallel LC circuit as shown in figure. So, this is a parallel LC circuit, inductance and capacitance circuit with internal resistances RL and RC. So, these are the internal resistance RL for inductance. So, RC is the internal resistance for capacitance. So, here in this lecture, so I am considering XC, capacitive reactance. XC is the variable element. By varying the XC, so what is the locus diagram of a LC circuit we will see in this class. So here LE is fixed, inductance is fixed and capacitance is varying. So for inductance, the resistance is RL, internal resistance is RL. For capacitance, internal resistance is RC. So this is a circuit diagram. So as usual, we know that alternating voltage of a fixed voltage V is applied to the circuit, and so with a frequency F or 50 Hz frequency. So here the total current entering into the circuit. So entering into these parallel branches. So I is the total current entering into the branches. So here this is the node or a junction point. Here the total current is divided into two branch currents. So IL is the current flowing through the inductance, a fixed inductance, and IC is the current, a capacitor current. IC is the current flowing through the variable element capacitance C. So this is the circuit diagram. So here you can see, so parallel LC circuit along with internal resistances as shown in figure. So consider here for drawing the locus diagram. So that is the circuit diagram we are considered for drawing the locus diagram by varying the XC element. As can be seen, there are two branch currents. So as I said, so the total current from alternating voltage source of V, the total current I is divided at a junction point. So these are the branch current. So this is the current through the capacitance. This is the current through the along with the inductance. So this is the total current divided into two currents IC and IL in a two branches. So similarly, locus diagram of the current IL or IC, depending on which arm is varied, and the total current I is also drawn by varying RL, RC, XL and XC one by one. So here in this lecture, I am considering the variable element XC. So that we will see in this explanation. So this is a locus of a current vector I in parallel or LC circuit when XC is varying from 0 to infinity. So this is the complete locus diagram of a current vector. That is the current vector I is the total current in a parallel LC circuit. So here you can see. So here we know that. So this is O and V is the voltage vector I am considering. So this is the voltage vector I am considering. So this is the voltage vector. We know that in a capacitor and inductor, in a capacitance, current is leading. So y-axis is the current vector, OI is the current vector, OV is a voltage vector. X-axis is a voltage vector, y-axis is a current vector I am considering. So here we know that current is leading. Current is leading with respect to the voltage in a capacitance or capacitance branch, and current is lagging. Current is lagging with respect to the voltage vector OV, voltage in a inductive branch. So in that inductive branch, current is lagging. In a capacitive branch, the current is leading with respect to the voltage vector. So this is the vector. So if you draw when xc is equals to 0, here xc is the variable element. I am varying from 0 to infinity. By varying the capacitive reactance variable element xc, so I am considering xc is equals to 0. When xc is equals to 0, the current is maximum, that is given by V by RC. So voltage by resistance, this is the current. So current is maximum when xc is equals to 0. The maximum current is given by V by RC. So that is all along the voltage vector at point B and C, BC. At point BC, so that is the thing. So if we are varying from xc value, variable element xc value from 0 value to infinity, from 0 value to infinity. So this is the current path traced by the current vector or variable vector. So IC is varying. The current IC flowing through the variable element capacitance or XC. So by increasing the variable element XC from 0 to infinity, the current is decreases. The current is decreases to 0 at XC is equals infinity. XC is equals infinity, the current decreases to 0. That means current is decreases. Current is decreases from maximum value of V by RC to 0 while increasing the XC to 0 to infinity. So this is a first point or locus diagram or locus of a current vector IC which is flowing through the variable element. So if you want to draw the locus of a total current vector, so locus of a current vector, that is the total current. So that can be drawn by the principle vector addition of a geometrical addition of a two vectors. So that is the principle which we are using in this case. So that we will see once you see the diagram. So as usual, I said the angle voltage vector OE at an angle of tan inverse XL by R, whereas the current is maximum when XC is equals to 0, that is given by V by RC. So this is the case. XC is increases from 0 to infinity, current is decreases from maximum value to minimum value, and the angle is 90 degrees. So the angle made by the variable element through the variable element theta c is equals tan inverse xc by rc. So here this is the case. So next, how to draw a locus of a total current vector. So if you want to draw the locus of a current vector, total current vector, we know that the sum of two vectors geometrically, we have to place one of the vectors at starting point. That is, here we will take a varying amplitude of vector IC. At the tip of the other vector, we will take a constant amplitude vector IL. And then joining the start of the fixed vector IL to the end of the vector varying vector IC. So if you want to draw the locus diagram of a total current I in a LC circuits, so this is the principle. So this is the principle we are using. So the principle is nothing but sum of two vectors geometrically. If you want to get a sum of the vectors to geometrically to get a sum of the two vectors. Here IC and IL are the two vectors. So IC I drawn locus diagram of a IC by varying XC from 0 to infinity I drawn. That is the path traced by the current vector IC. So that is the locus of a variable element XC, that is nothing but a current vector. So if you want to draw a total current, if you want to draw the locus of a total current, so we are using to sum of the two vectors geometrically. So geometrically we have to take sum of the two vectors. So how we are taking the sum of the two vectors geometrically? So first we have to place one of the vectors starting point. You consider one of the vectors starting point, here variable vector IC, and at the tip of the other vector here is the constant amplitude vector IL. IL is a constant or other vector. So variable vector is the IC. So starting point of fixed vector variable vector IC and tip of the other vector. So this is the case. So this is the principle. We can get the locus of the total current vector OI by shifting the IC semicircle starting point O to the end of the vector OIL, keeping the two diameters parallel. So here the diameter is a V by RC is the diameter. So with this diameter we have to drawn IC locus of a variable element XC IC. So parallel to this one we can add the locus of a total current vector. We can draw the locus of a total current vector resulting semicircle IL BT shown in a figure. Dotted lines is the locus of a total current. So that I will shown in a locus diagram. So this is the total locus diagram. So this is the locus diagram of IC. So IC it is a semicircle by varying the XC is equals to 0 to infinity. So this is a IL vector. IL is this one. So here I am starting. So this is a OI is a total current. So by adding this IL and on to the tip of a variable vector. So with a diameter of V by RC. So this is the diameter which we are taking. So same diameter. So this is the diameter of a locus of a total current is parallel to the diameter of a IC circuit. So vector IC. So V by RC is the diameter of a vector IC. So if you want to draw the locus of a total current I, so same diameter I am considering. V by RC is the diameter. With this diameter I am tracing. So this tip of a IL fixed current onto the variable current vector IC. So by this, with this same diameter of IC current, I drawn this locus of a total current vector I. So this is the total current vector. This is a complete locus diagram of a LC circuit by varying the variable element called XC. So this is all about the locus diagram. How to draw a locus diagram of a current vector I in LC circuit by varying the XC. So this is a reference from a Google. So thank you everyone. Thank you all.